Hi everybody, my name is Jacob Lewis and this is my KI4 presentation. So as we all know, this is the signal transmission circuit, and today we're just going to be talking about this area of the circuit that's located inside the red box, which includes the amplifier, a mixer, another amplifier, the bandpass filter, and the antenna. To start off, we're going to start off with the amplifier. Now this amplifier is generally just to amplify the input signal located by the box A. And this can be done using a common source amplifier design that we have used in 332. Now this common source amplifier has a gain of GM-R out, but in this case, because IDS is so small and the R0 is basically 1 over lambda times IDS, we can say our R out is equivalent to RD. So if we wanted a gain of 10, we could just say that GM times RD needs to be around 10. Now for a common source amplifier, there are a couple of drawbacks. So for VSAT, the output swing is limited at a maximum by VDD and at a minimum by VSAT. So if you raise VSAT too high, then this wave is going to be clipped off on the bottom half by that too high VSAT. For IDS and width length, if you were to increase IDS, it really does help increase the gain, but increasing IDS can be detrimental to your overall bandwidth. So if you care about bandwidth, be careful about increasing IDS. In addition, if you increase your length, it does increase your R0, but that doesn't have a very big effect on your gain, and it decreases GM, so it's not suggested to increase your length. For RD, if you were to increase your RD, that decreases the amount of voltage, DC voltage, at the output, which also can mess with your output swing. So this is our circuit again, and next we're going to talk about the mixer. So a mixer essentially multiplies two time domain signals together. Now in frequency domain, that means that it convolutes the two frequency domain signals together. Now as you can see in the bottom left, that's a frequency domain representation of just your regular voice signal. And in the bottom right is a time domain representation of a carrier signal. Now if you convoluted the bottom left with the frequency representation of the bottom right, you end up with something along the lines of this. And that's your output, Y of j omega. And as you can see, you have the voice signals located at two center frequencies of omega naught of the carrier signal. Now basically, this means that you can fit these small voice signals in a super high frequency omega naught, somewhere around 900 megahertz. And you can pack these in, which is how cell phones communicate with us, each at different omega naughts with different voice signals. So this is just kind of a general picture regarding the voice signal with a carrier. So the first graph is just an unmodulated carrier, regular high frequency signal. The voice current shows, just like my voice is right now, up and down, low points, high points. And then when you multiply those two signals, convolute the frequency domain, you get the modulated carrier, which is what the antenna is going to receive. So next we go to the PA. And the PA is really just for it's a linearity amplifier, and it's really worried about power efficiency. After that, we have the bandpass filter, like the arrow shows. Now, these are just a couple of basic filters. So a low pass filter has a resistor and a capacitor, and the capacitor basically is a short when frequencies are super high. So then the output doesn't see any current because the capacitor is shorting out the output. And at low frequencies, the output's going to see all of the current that goes from B in. Contrary, in the high pass filter, when you're in a really low frequency, the capacitor acts just like an open. And in an open circuit, then the resistor and V out doesn't see any current at all and won't see any signal. Now what you can do is you can really combine these two signals together, or use a RLC network to create a band pass filter, which passes a certain band of frequency. As seen by the top right, if you input a signal into a low pass filter and then input into a high pass filter, you're obviously going to get some specific band, depending on the filters you use, that would become a band pass filter, and that would be your signal output. Now this can be done using the bottom left figure. So you have a capacitor, which would be open during low frequencies, and you have a inductor, which is open during high frequencies. So during both of these situations, no current, no voltage reaches the output, so the out doesn't see anything. Now in the bottom right, we have just your regular old basic bandwidth of a bandpass filter, and you can see the center frequency and the 3 dB cutoff point. So next we're going to talk about the antenna, what's on the far left. Now at the top we have just your basic carrier frequency. This is, like I said before, your high frequency signal. You have your voice input signal that you're going to be multiplying the carrier with, and then you get your modulated result, and this is what's going to be sent to these antennas. So in the bottom right, actually, we have a loop antenna, and these antennas are mostly used for receiving low frequency signals, AM, radio, things like that. On the left, we have an example of a dipole antenna, and this is actually what's used inside of a cell phone. Now, this is another example of a dipole antenna, and the red area is the highly concentrated electromagnetic wave propagating out from the antenna. Now, we know that if you orient your antenna parallel, so 0 degrees or 180 degrees, then that's how you're going to get a maximum level of voltage on your receiving antenna. But if you orient your receiving antenna at a 90-degree angle, so orthogonal in any direction, you won't actually get any voltage on that antenna, and it will not pick up any signal. We know this from Faraday's law because if there isn't a change in the B field, there's no flux, and if there's no flux, there's no induced EMF, and if there's no induced EMF, then there's no current, no voltage that the antenna receives. Overall, this is the circuit, and it was really cool in this KI just to learn about the amplifiers in 332, how that relates to the 311 perspective of a mixer, back to another amplifier, bandpass filter, which we learned how to implement in 332 and what it does in 311, and then the antenna wave propagation in 342. This KI was definitely worth my time. Thank you.